everybody. Coming to you with another one of these mixed radical rational exponent type equations where the index is actually fraction, which takes some getting used to. Now, what we're given here is that we have a unique natural number solution. It turns out this thing actually has complex solutions, and I think an irrational solution, but it turns out it also has a single natural number solution. And by that, I mean numbers like 1, 2, 3, 4, 5, or sometimes called the positive integers. Now, I just want to give you kind of a concrete example that kind of dictates the strategy here. It's just based on something fairly elementary. Let's say that we had the cube root and again, this is something you could just solve by inspection, but just trying to illustrate what we're a property here. So if we have the cube root of 8 equals to x. Okay, by inspection, you can see that solution. But another way of looking at it is just put the cube root of 8 inside the parentheses here. All right, and then you get you cube it, right, to remove the radical. Cubing and cube rooting are inverse functions, but you also have to cube the right-hand side. All right, and so you would get x cubed, right? Okay, but this means that 8 is equivalent, 8 is equal to x cubed, right? And of course, that has a solution x equals 2. Okay, so now you may think that's the long way to Rome, you know, but I mean, it's what we're doing to solve this equation. What we have right here is the very same process. I just took this expression that we're trying to find a solution to, and I raised it to the n over n minus 6 power. You see I did that to both sides, y'all. If you take a look, this object right here gets raised to the fractional exponent n over n minus 6. The very same thing right here. Okay, and for the very same reasons that we did it here, it makes doing this makes this index disappear, right? And so you see from here to here is the magic here. So right here, all of this stuff results in nothing being left but this radicand over here, all right? And so you have to do the very same thing also to the right-hand side, all right? Now, so this works out rather nicely because at this stage, all you have to do is just apply the laws of exponents. Now, it turns out all you have to do, since these are unique prime factorizations, all you have to do is apply the laws of exponents to just one of the prime factors, all right? And so that's exactly what I did right here. I equated 2 raised to the n equals to, when you apply this laws of exponents right here, it says we multiply the 5 against the n over n minus 6. And so that's what happened right here, all right? And so since exponential functions are one-to-one, we can equate the exponents, which is exactly what this statement says right here. We equate the exponents n equals to 5, n over n minus 6. I didn't quite finish this thing off, but this would imply that n squared, if we subtract 5n from both sides, we get n squared minus 11n equals to 0. And so we get 2 solutions. Here we get certainly 0 is one solution, one apparent solution, and then 11 is the other solution, right? I mean, that's just by inspection. You could factor an n out of this and get n times n minus 11 equals 0. We would get 0 and 11. Now notice here, 0 ends up corresponding. If you take a look at placing a 0 right here, that doesn't have much meaning. Taking the 0th root of anything, of something, doesn't make sense as far as I know. So now it would make sense here because you would get 1, 2 to the 0 is 1, 3 to the 0 is 1, but 1 does not equal to this number over here, right? So in the event that the index being equal to 0 makes sense, you could reject it based on what I just said. But I don't think the index of a radical being equal to 0 makes sense in any context that I'm aware of. But in any event, we're going to rule out this solution right here. We're going to rule out this solution in n equals 11 is the natural number solution we were seeking. And you can I'm not going to check it, but you can check it. It does work out pretty nicely, just kind of using this with numbers in there, basically, So n equals 11 is the answer, ladies and gentlemen. Let me know what you thought another time.